Okay, welcome back. We're going to pick up where we left off. We were talking about this reaction of iron oxide becoming iron. By the way, reduction reaction. So there's a relationship here to redox that we're going to take a look at in chapter 18. But in any event, we said that we calculated that this was endothermic, and as we went from 25 degrees Celsius to 500 degrees Celsius, it became spontaneous, which makes sense because, again, heat favors the endothermic process. So the next part of the problem was, now that we know what our delta G is for this, at what temperature does this become spontaneous? And that's the key. What temperature does it become spontaneous? So the threshold between spontaneous and non-spontaneous is when delta G equals 0. So for this one, we have the Gibbs equation, and then we're going to solve that for the temperature at which we get when this thing starts to become spontaneous. So the key to this is that you have to recognize that delta G here is equal to 0 under those conditions. We had already calculated delta H and delta S in the previous problem, so we can substitute that in and solve, and we get 725 Kelvin or 448 degrees Celsius, which is a little different than their answer, again, because of the updated delta H and delta S values. Not by much, though. Okay, so what about this nonsense? Can we calculate delta G naught from delta G naught formation values? Again, the key here, though, is you have to recognize that in the formation values, they're talking about creating 1 mole of the compound from its elements in its standard state. So two things there. One, we're only talking about 1 mole of the compound. And two, it has to come from its elements in their standard state. In other words, whether they're solids, liquids, or gases at 1 atmosphere and standard temperature. But we would do this the same way we did delta H of formation values. Again, the summation of the products minus summation of the reactants. And I'm not doing an example of that because we have done that sort of thing in the past. All right, calculation of delta G, which means what is the spontaneity under those conditions versus the spontaneity under standard conditions. There is a relationship there. And delta G naught plus RT natural log of Q. So Q would be the Q versus K. So we're looking at the equilibria conditions we have. And RT, gas law constant, is there. And it's an energy value, so normally it's 8.31 joules per Kelvin, but this is going to be in kilojoules because our delta G values are in kilojoules, so they list R as 0.00831. Again, that doesn't mean that we're dealing with gas reactions. It doesn't mean that we're dealing necessarily with ideal gases, but we're dealing with ideal behavior for this relationship. Something to point out, that when you are dealing with Q equal to 1, that gives you a natural log of 1, which is 0, and that eliminates that entire term from this side of the equation. And if we do that, then that is the condition under which delta G is equal to delta G naught. So again, we are dealing with Q, so whatever values that we have for products over reactants, remember this is the mass action expression. I only show it because they also talk about this as the activity of the conditions. In other words, if Q is greater than K, then that means we have too much product and the system is going to go to the left in order to reach equilibria. And if we have where Q is less than K, then we have too much reactant and Q is going to go forward until we reach equilibria. Okay, so here's the question. What is the delta G naught for lead 2 chloride ionizing in solution, which means dissolving by ionization? So that tells me that we are dealing with some sort of KSP problem. And they give you the value for this. It's positive, so it's non-spontaneous under these conditions. And they say that the lead and the chloride concentrations are both 1 times 10 to the minus 3 molar. So I know that we're dealing with some sort of Q situation here. Calculate delta G of this reaction at 25 degrees C. Okay. Okay, so a comparison between delta G and delta G naught. All right, delta G naught. It's going to be this equation, delta G naught plus RT natural log of Q. I know that KSP is lead times chloride because we're dealing with this process, right? Lead, chloride produces lead 2 plus 2 moles of chloride. So KSP is lead times chloride squared. And now I can substitute in the values that they gave me for Q, and I get 1 times 10 to the minus 9. Okay, fine. Now that I know Q, I can substitute into the original equation for delta G. They gave me delta G naught at 27.3 kilojoules per mole reaction. Gas law constant, 298 K temperature, and I'll take the natural log of 1 times 10 to the minus 9, and when I simplify all that, get negative 24.0 kilojoules per mole. Okay, now the relationship between delta G and KEQ. A little different. Delta G naught is negative RT natural log of K. So a couple things they want you to know about this. Besides, if they give you a value for K, you can substitute into delta G naught. Or I'm sorry, substitute in and get delta G naught. But if K is greater than 1, then you're going to wind up with a negative value for delta G. So this is going to be spontaneous under standard conditions. And if K is less than 1, then delta G is non-spontaneous under standard conditions. Now, bear in mind, just because a reaction has a small KEQ doesn't mean it's going to be non-spontaneous. It just means it's going to be non-spontaneous under standard conditions. Certainly, those reactions or processes can take place in a different environment spontaneously. They're just saying, all right, what's going on here compared to standard conditions? And then when Q is equal to 1, delta G naught is equal to 0. Now, suppose they give you this for K and they want you to get delta G instead of delta G naught. Well, we can use K to get delta G naught, and then we can go back to that other equation where delta G is equal to delta G naught plus RT natural log of Q, and figure out delta G from there. All right, so they give you this problem. We got Ka for a given process, and they want us to calculate delta G at 25 degrees Celsius when we have those certain ion concentrations. Right? They give us the acid and the conjugate base at 1 times 10 to the minus 5 molar, and then the original acid at 0.1 molar. Okay, we can do this. First thing I know is that they want delta G from this. Okay, great. But in order to get delta G, the only relationship I have is this delta G equals to delta G naught plus RT natural log of K. So they're giving me two things in the problem. They're giving me K at 1.35 times 10 to the minus 3, but they're giving me these ion concentrations which are indicative to, looking at a condition involving Q, and that's done for a reason, because what you're going to do is you're going to use delta G naught and use K to get delta G naught, and then once you know delta G naught, we can substitute that into this expression. Delta G equals delta G naught plus RT natural log of Q. And like I said, they've given us values in which we can figure out Q. All right, so here's what I did. I set up my Ka, acid times conjugate base over original acid, and I calculated Q by substituting in the values that they gave me for Q. Then I substituted that into delta G equals negative RT natural log of K, and I got positive 16.4 kilojoules per mole. And that makes sense because we said delta G naught, when you have a small value for K, is going to be non-spontaneous under those conditions. Okay, great. But we don't have those conditions. We're not at equilibria. We have concentrations which are not indicative of the values for Ka. So now we can go and we can substitute delta G naught plus RT natural log of Q. So I substituted in those values. Again, Q is going to be acid times base over acid times conjugate base over original acid. And I didn't work that out. I just went ahead and simplified that to be 1 times 10 to the minus 7. When you work that out, that's what you'll get. And then I simplified the two expressions and got negative 23.5 kilojoules per mole. Okay, these practice problems I'm going to do separately on a different show. I'm going to go work them out in advance so it goes a little smoother, and I'll see you on the next video.